Alright guys, so this is problem number 4. It says the gate AB is 8 meter wide. Determine the hydrostatic force on gate AB with a density of water equal to 1 megagram per meter cube. Okay, so I'm not sure how many of you guys are here are taking fluid, which is CE 2200 next semester, but if you do, but if you don't, then I highly suggest you take that course. It's very fun, interesting. Okay, so for this kind of problem, since this place right here is not directly vertical or directly at an angle, but it's connecting the both. So meaning that since this is like this, meaning that there will be two hydrostatic force on the plate AB. The first one would be a rectangular load, and the other one would be triangular load. Okay, and this is the free surface right here, which by definition, free surface, at free surface, the pressure will be 0, and the weight will also be equal to 0. Okay, and we know that the formula for the pressure is equal to rho multiplied by the gravity multiplied by the vertical distance v. Okay, and then the weight is equal to the width of the plate multiplied by the pressure. Okay, so here we have two loads right here. So if we consider this distributed load into a single point load, then we know that for this rectangular load, the point load is directly in the middle. And then for this triangular load, the load would be 2/3 of distance from B and 1/3 of distance from A. So let's call this F1, let's call this F2. Okay. So first, let's see if we can find the pressure and the weight at point B. Change the color. So at point B, PB, pressure at B, which would be rho GZ. So be 1 megagram per meter cube multiplied by 9.81 multiplied by C, which is 5, and we're gonna get 49.05 kilonewton per meter cube. Okay, it will be kilonewton per meter cube, not newton per meter cube, because we consider that density of water is a megagram per meter cube, not kilogram per meter cube, if that makes sense. Okay. All right, and then we have a weight of B right here. Weight of B will be the it'll be the width of this plate B multiplied by the pressure PB. But since we know that AB, which is this one right here, is 8 meter wide, but we don't know that what's the width of from the free surface to B. But let's just assume that it's going to be 5 as well, because the only thing we know that is the vertical distance from the free surface to B is 5, which that's the Z, but we don't know that what's the width of B. So let's just assume that it's going to be equal to 5. And then multiplied by PB, which is 49.05. And you're going to get that WB will be equal to 392.4 kilonewton per meter squared. Okay, next thing now, let's do analysis at A, PA, same thing. F1 multiplied by 9.81 and then multiplied by Z. You have to, that's the vertical distance, okay? So even though this place is tilted, but you consider the vertical distance, so it would be 5 plus 4, so you combine and then calculate that, you're gonna get 88.29 kilon, 88.29 kilonewton per meter square. My bad, guys. This should be square right here because this is pressure, not density. Okay, and then WA, since the width of AB is given, we know that that's A. Then you multiply by PA, which is 88.29. You're gonna get 706.32 kilonewton per meter square. Okay, so hold on. Oh, okay. So we know that that's my mistake, right? It shouldn't be meter square because the unit for this one's meter and the unit for this one's kilonewton per meter square. So this cancel out, so it'd be just kilonewton per meter. Yeah, that was my mistake right there. Okay, so we know that at B, this point right here, it has the total distributed load, which is the way it will be 390, 392.4. And then at point A, this one right here will be 706. It's not clear. So right here will be 706.32. Okay, so let's find out what F1 and F2 is, which that's the hydrostatic force. So we know that for F1, okay, since the F1 is a triangular distributed load, we know that the equation for that will just basically be the area of that triangle, which will be 1/2 length times the width. Okay, I mean 1/2 the load times the length, which the load right here will be 706.32 minus 392.4. Then the length will be this length right here. How do we determine that? Well, by Pythagorean theorem. Okay, because we know that this is 4, this is 3, as you can see right here, which meaning that this one right here will be 5. Okay, so that's the length for F1. And then if we calculate that, we're going to get F1 will be equal to 784.8 kilonewtons. And then for F2, since it's a rectangular distributed load, we know that to find out that single point load force, it will be simply just the load multiplied by the length. You don't have to take that or have into consideration. So basically 392.4 multiplied by 5, you're going to get F2 will be equal to 1962 kilonewtons. Okay. And then we can find the F1 with the resulting hydrostatic force will be simply just F1 plus F2. And we're going to get 2,746.8 kilonewtons. Okay. All right, guys. So this is, like I said, will be the type of hydrostatic force problem that he's going to give to you on the exam, because I also assume that it's a multiple choice also. I don't think he will give you a very difficult problem on those kind of problems. All right, I'll see you guys in problem number 5. All right, guys, so this is problem number 5. So parallel to the problem, I always saw the table and also some important stuff that I had to write out when I was working on the problem, but it takes time to write them out. So I'm just going to write out right there. Okay, so the problem says the aluminum shade, the aluminum shade for the small high intensity lamp shown has an uniform thickness of 1 millimeter. Knowing that the density of the aluminum is 2,800 kilogram per meter cube, the mass of the shade is closest to what? Okay, so it's asking us to find out what is the mass of this shade area right there. So we know that for area of this this kind of 3D century problem, the area is equal to 2 pi y bar L, where you can say that the y bar is equal to the r radius. Okay, and then so I have this set up right there for you. So first we know that if you zoom in and looking at this one right here, so this one right here basically just half of this aluminum right here. Okay, so I have so this is my segment 1, segment 2, segment 3, and segment 4. Okay, so that's right now. So 1, 2, 3, and 4. And the length for segment 1 is based simply just a 13 millimeter. Okay, but for segment 2, we have to do the Pythagorean theorem to find out what is length right here. Okay, so basically just do square root of 32 squared plus 3 squared, and we're going to get 32.14. Yeah, same thing for segment 3. Square root of 8 squared plus 12 squared, I'm going to get 14.42. And then segment 4, basically just the square root of 28 squared plus 50, I mean not 55 squared, and we're going to get 28.44. Okay, so we have that. And then the y bar. Okay, so this is the y-axis. This one is the x-axis. We know that the y bar will be simply from the axis perpendicular to, basically the y bar is perpendicular to the x-axis. Okay, so for segment 1, the y bar would be right here, which will be half of 13 millimeter. So simply just 13 divided by 2, we're going to get 6.5. And for segment 2, we have is the y bar will be right. It'll be just it'll be 13 plus the half of 3 millimeter. So 13 plus half of 3 millimeter, so we get 14.5. Same thing for segment 3. So it'll be 13 plus 3 and then plus the half of 12 millimeter. So 13 plus 3 plus divided by 2, and get 22. Then for segment 4, same thing, 13 plus 3 plus 12 plus half of 5. I'm going to get 30.5. Okay, and then this column, the last column right here, basically just do the length multiplied by the y bar. So we know that for segment 1, it'll be 84.5. For segment 2, it'll be 466.03. Segment 3 will be 17.24. And segment 4, 867.42. And then basically just sum all of them together. We get 1735.9 millimeter squared. Okay, so at this point we can compute our area. So area will be 2 pi, and then summation of y bar L will be 2 pi multiplied by 1735.9, and we're gonna get that the area will be 10,902.51. Okay, so right now that we find out the area, but the problem asking for the mass. Okay, and then we know that for mass, the equation for mass is equal to the rho times multiplied by the volume. Okay, and then the rho is getting right here. The rho, which is the density, is 2,800 kilonewton per meter cube. So we right now that we need to transition from area to volume. How do we do that? Well, the thickness is given. So the thickness is 1 millimeter. So simply just say, so the volume will be equal to area multiplied by the thickness. So it'll be 10,902 plus 51 multiplied by 1 millimeter. So it's simply just 10,902 plus 51 millimeter cube. Okay. Then right now we can compute our mass. So mass equal to the rho, where the rho is 2,800 kilonewton per meter cube. But we need to turn that meter cube into millimeter cube. So it'll be equal to 2,800 kilonewton per millimeter cube times 10 to the negative 9. Not bad. Should be times 10 to the negative 9 kilonewton per millimeter cube. Okay, so 2,800 times 10 to the negative 9 multiplied by the volume. And we're going to get that the mass will be equal to 0.0305 kilograms. Okay, so that's all for this problem, and I'll see you guys in the next problem.